Let's now investigate Stuxnet architecture. Stuxnet itself mainly consists of a large DLL file. DLL stands for Dynamically Linked Libraries. And these are, they're like executables, but they don't have a way to be executed. So they contain functions, but not a main function that will execute the file itself. The DLL file will have different exports, and that will be different functions with different things the functions are doing, and the resources that will be data, will be other files, for example, that will be dropped by Stuxnet during the infection and loading process. It also contains two encrypted configuration blocks, and we'll see in a few slides what is a configuration block. So the dropper of Stuxnet would include all above components in a section named stub, and this is where the STU part of Stuxnet comes from. And when the Stuxnet, the dropper is executed, then once Stuxnet is executed, then the dropper will extract a DLL, map it in the memory as a module, and will call one of these exports, the export to start, that will be export 15, the initial entry point. There are different ways to call these exports. It could be either reading the executable template from its own resources. Again, DLL has its own resources as well. And then it would inject the template into another process and execute it. So there are different ways Stuxnet could be loaded. On the right-hand side, you see the table with all the DLL exports. And the ones that are of interest now will be export 15, that's the initial entry point, the first one to be called, and entry 16, that would be the main installation of the Stuxnet malware. So when you load DLLs, the antivirus you may have installed in your computer can detect that something may be going wrong with that DLL loading. So there are ways that behavior can be checked, and then given weird behavior on behalf of the DLL, the antivirus may block the execution, eventually stopping the malware from propagating. So Stuxnet was anticipating that. And to bypass those protection mechanisms that specifically monitor these DLL loadings, the load library calls from the API, Stuxnet would call those libraries with a specially crafted name that does not exist on disk, and then the load library would fail. So to do that, Stuxnet had a rootkit, and it affected this file entity DLL.dll. So whenever you were trying to load the library call would fail, so the antivirus mechanism were not able to do further behavior investigation in those loads. However, Stuxnet had hooked into this DLL, and then it would load this specially crafted file name to execute parts of Stuxnet, because Stuxnet again was DLL calls, and to ensure that the antivirus wouldn't monitor those calls, it would intercept the load library and ensure that the antivirus wouldn't check further. So these file names, these specially crafted file names, would have this pattern, kernel 32 DLL ASLR, and some hex value, same with shell. They look like legitimate system files. And the function hooked within that DLL to monitor the request would be the open file, as we just said, or the close file, and 4 more functions in that dynamically linked library. So, injection. Stuxnet would check for the antivirus product installed, and given what was the type and the version of the antivirus product, it would inject itself in different ways. So Stuxnet can inject itself through different ways. One would be an existing process. Another one would be a newly created process, or it could have been a Windows, some pre-selected trusted process, some Windows process, or some security product. So you see, for example, on the table, like if the Kaspersky antivirus was installed, then the injection target would be that Windows process, right? The LSASS. If it was another version of the antivirus, it would actually install directly using the antivirus itself. McAfee would be a trusted process. Specific antivirus like the eTrust V5 to V6, Stuxnet would fail to inject because of the mechanism that these antivirus were using to check for viruses or malware. So you see it was checking for the security products, and it will have different injection targets. So to find the security product installed, it would look both at which processes are running and within the registry. So in the registry, you have information about installed products, and in case it found a non-bypassable one, like this one, the eTrust v5 to v6, it would abort the execution. Then it would also determine whether it needs to use 0-day for privilege escalation. So in case, it depends on if the infected process had privileges or not. If it didn't have advanced elevated privileges, then Stuxnet would employ a 0-day vulnerability to elevate privileges to kernel or administrative privileges. So for this, the exact process you can read more in the manual that Symantec has produced about exactly how Stuxnet work. But it was the Stuxnet would be loaded in this .verif section, and then the entry point target should fall within that section. Stuxnet will place a jump to it and jump to the desired entry point of the injected code to start the execution after injection. This was another mechanism for also bypassing the behavior blocking security products, as we saw before. If the antiviruses were looking at the behavior of the DLL and find weird behavior, then they would block it from further executing. So this way would allow also bypassing those behavior blocking mechanisms. All right, so I mentioned before, Stuxnet included two encrypted configuration data blocks, and these blocks contain all the values used to control how Stuxnet would act on that compromised computer. So whenever a new version, Stuxnet would update itself, so a new version would come in. And whenever a new version would be created, then the configuration data would be updated to have the right versioning of Stuxnet. And whenever two Stuxnet infected computers would communicate, the newer version would override the older version, no matter which way that was. So this computer, there was also a computer description block appended to that configuration data block, and that would be information about the infected computer. And this block would contain information such as the computer name, the operating system version, major and minor, specific flags used by Stuxnet, a flag specifying if the computer is part of workgroup or domain. Stuxnet would also record the time of infection, as we saw in the previous video. Compile time to infection time. Stuxnet wanted to know exactly when infection happened, so they understand how much time it took to propagate further. Computer name, domain name, and then the file name in case of Siemens, the Siemens software being installed in the computer. It would also include the file name of an infected project file. So the attackers would know exactly the file name that was infected. So essentially, this configuration data block was housekeeping for Stuxnet. Installation was performed by export 15. I mentioned before that the first function call, the first export call from the DLL would be export 15. And it would start by checking the configuration file and see whether something is wrong there, and it wouldn't start if something was wrong in the configuration file. If the file was okay, it would check whether the computer would be a 64-bit or a 32-bit one. If it was 64-bit, it would also abort. It was only affecting 32-bit machines. Then it was checking the operating system. It was affecting specific Windows machine and specific versions of Windows. So if that operating system was okay, it was within the versions that would be infected, then it would proceed, and then it would check administrative rights. If it had admin rights, it would continue with the infection to check the antivirus that was installed, and given the antivirus version and brand, it would choose the process to infect. It would infect the process, and then export 16 would be called, that will continue the execution of Stuxnet. In case administrative rights were not present, then Stuxnet would use a 0-day to elevate privileges. So here would not be writes, and it was a different 0-day given different Windows versions. If it was XP or Windows 2000, it would use a different 0-day compared to Vista and Windows 7. So after the OS was checked, then a different vulnerability will be employed, but they all result in the same thing. A new process, Stuxnet running in a new process with elevated privileges, either CSRSS or as a completely new task through this 0-day vulnerability here. So and then the previous process will just exit. So no matter what the path is, Export 15 ends with a process running with elevated privileges and the ability to call Export 16. So Export 16 will be called either here, here, or here. To further understand how Stuxnet managed to elevate its privilege and run as administrator, let's check this specific vulnerability exploited by Stuxnet for privilege escalation. So this has been reported as MS10-073, and it was a 0-day vulnerability in win32k.sys that was eventually patched in October of 2010, and that vulnerability was used by Stuxnet for privilege escalation. So the vulnerability was using some part of Windows XP where a user-level program could load a keyboard layout, but then when this would happen, and you would select which layout you wanted to have, English, or, Greek, or some other language. Then you would give an integer to the layout file that would index a global array of function pointer. But there was no bounds check in that array. So you could have actually select a layout that didn't exist. It was not part of that array. In this way, because the integer was just used as an index, essentially you could call any function. You just have enough offset from the entry point of this array to wherever you wanted to jump to, and the function would be executed from that offset. So in order to exploit that, the only thing you need to do is to find the pointer to that array, to that global array, and then find a pointer to somewhere you can inject your own code, inject your code, and then try to jump from the beginning of that array. The array had some size, but you could jump to any part of the array after it. So if your memory, you have the array, and then you put your code after the array, then you can jump far enough to enter your own code, and in this way, this code you just execute it, will run with admin privileges, because when you call this keyboard layout, this is a kernel process. So running this will run your code with administrative privileges. And now you can have control with admin privileges, and you would call export 16. That would be the next step in Stuxnet loading process. So export 16 starts with the assumption that you have elevated privileges within the operating system. And it starts by, again, checking the configuration file like the previous one, export 15. And if it found to be okay, then it would check for a kill switch. So it was a specific registry key that if that had a very specific value, this one here on the slide, then Stuxnet would exit. So it was more of a kill switch to ensure that computers that the adversary didn't want to be infected, they wouldn't be infected, because Stuxnet would stop propagation, would stop loading if that special value would appear in one of the registry keys. If that value wasn't there, then it was also another check for the date. So it would also work only when the date was, in this example, less than 24th of June 2012. So it had an upper limit in how long it would work. If it was within the deadline, then it would start checking the operating system again and do some way to elevate some privileges for this global mutex communication. This is becoming a bit more technical. After these global mutexes for communication were established, then it would create files. Remember, at this point, well, from the beginning of it, Stuxnet runs as a kernel module. So it can do whatever it wants to the system. So it would create new files. These files were actually Stuxnet files. We'll see later what they'll be used for. Another date check, and then it will decrypt, load itself from disk, and then call export 6, one of the other exports in the Stuxnet, in the DLL, and see whether, and it was checking whether what's already there, what is newer. Remember, Stuxnet had this peer-to-peer mechanism. Whenever it was infecting a new computer, it was checking whether Stuxnet was already in the new computer, and it was checking what version was newer. And given the version number, it would proceed to update to one or the other. After the versioning check would go through, then it would also extract two files, other files from before. So these are related to the PLC, but these are driver files. These were the rootkits to ensure first that Stuxnet would hide itself from the calls to the operating system to show specific files, and also be part of a driver that would load in the beginning when, if you restart your computer, these device drivers will ensure that Stuxnet will run again after the computer has been rebooted. So the resources have been now written, and the device drivers would be in place, and then these will be used for rootkit service, and then it would start the propagation process, either infecting removable drives. If something was connected to that computer, a USB drive was detected, then it would install itself in the computer. Otherwise, it will try to find step 7 projects and try to infect step 7 projects by calling export 2. So after this would happen, it will call export 32 and would exit to continue with the Stuxnet malware propagation process.